Okay, let's talk about the factors that do favor E2 reactions and the factors that favor E1 reactions. We're going to start by looking at the base. In an E2 reaction, since the base is involved in a transition state and you never actually form a carbocation, there is no restriction as to what kind of base you can be using. In fact, you want to use a better base, and a better base is a stronger base. A stronger base is, from the point of view of this energy reaction coordinate profile, means that your base, your Y minus, is going to have to be higher in energy. That's what it means to have a better base. It's more reactive, and to be more reactive means that you are a stronger base. So basically, the act of raising the energy of the reactant by itself lowers the activation energy of the reaction and makes the reaction go faster. So you want to use stronger bases to favor your E2 reaction. In regards of solvent, the story is very similar to the substitution reactions, in the sense that if you do have Protic solvent, the Protic solvent is going to coordinate to the cation, but it's also going to coordinate to the anion, aka the base. And in doing so, it kind of like forms a cage around it that makes it more difficult for the base to reach onto the alpha hydrogens to carry over the elimination. So generally speaking, Protic solvents that have the OH bond or the NH bond present are going to make it more difficult for your reaction to go forward, simply because the solvation of the anion or the base leads to a stabilization of the reactant. And stabilizing the reactant means that you're lowering the energy of the reactant, which in and of itself means that you're increasing the activation energy. So in E2 reactions, you want to avoid using Protic solvents, and if at all possible, aprotic solvents are the way to go, because that will leave your base naked. And leaving your base naked means that you're going to make it definitely way more reactive. You're not stabilizing it at all. You're giving it its full potential to react. So this automatically raises the energy of the reactant, and it also lowers the activation energy. Now, in terms of the substitution of the alkyl halide, now this was a big factor in substitution reactions. But in elimination reactions, at least the E2 reaction, they don't really play a huge role. And the main reason why this is simply because the base is not attacking the carbon center that bears the leaving group. The base is attacking the group next to it. So it doesn't really matter if this carbon is primary, secondary, or tertiary. The elimination is going to happen regardless, because it's happening on the neighboring group, right? So even though there could be shenanigans going on here in terms of sterics, here on the left side, everything's cool. So the basis attacks there, and you can form that. And there is a small increase in energy, but it's small enough that doesn't really affect things all that much. So you can definitely do an elimination with primary, secondary, and tertiary electrophiles. The one thing you can never do, however, is to undergo an elimination with a methyl halide. And the reason why is because you need two carbons. You need to have a neighboring carbon to the one that bears the leaving group for you to do an elimination. So if you do have a methyl halide or a methyl with some leaving group bound to it, that's going to be guaranteed to undergo an SN2 reaction, never E2. Okay, finally, much like your substitution reactions, the leaving group, you want the leaving group to be good. If the leaving group is not good, it's going to be difficult for you to carry the reaction. And having a good leaving group means that you are lowering the activation transition state, the transition state altogether, because it's easier to break this bond. So you're facilitating this process at the transition state, and in doing so, you're lowering the activation energy itself. So yeah, make sure that you have a good leaving group. So if you look at the table for E2 reactions, the substrate could be primary, secondary, tertiary. Definitely not methyl. The base, you want it to be as strong as possible. The solvent, you want it to be aprotic. The leaving group, you want it to be as good as possible. And the temperature, you want to heat up the reaction for sure, because you want to help out the elimination process via the entropy, right? And if you increase the temperature, the fact that eliminations have positive entropy means that you're going to favor the elimination route, right? So I personally think that if you go beyond, 40 degrees, like if you get to 50, 60, 70, if you reflux the reaction in, a high boiling solvent, you're probably going to undergo an elimination reaction. But keep this in mind, your methyl halides will never be able to undergo elimination. I can't really highlight that enough. All right, now looking at the E1 reaction, we have to keep in mind that two steps happened in the process of this reaction. So we are going to have an actual intermediate form, which is the carbocation. The first step is the one that limits the rate of the reaction. This is the limiting rate, the one that has the highest activation energy, and it is a process of the carbon leaving group bond being broken, leading to formation of the carbocation. It's at that point that the carbocation interacts with the base. The base removes the alpha hydrogen, producing the alkene, and that's a lower energy profile altogether. Now, the deal with the base is that because it does not interact at the rate determining step, it's really not going to speed up the reaction whatsoever, because at most you might be able to like maybe mess with this second activation energy, but because this is not the highest activation energy, you still are stuck having to go through the bottleneck of this process. But the other thing about the base is that a carbocation is being formed in this reaction, and a carbocation is a very strong acid. Technically speaking, the conditions under which an E1 reaction takes place are acidic, so you cannot have a remotely strong base present in your solution. That will make it very unlikely for you to form the carbocation. So what this basically means is that your base is going to be a crappy base pretty much every time. It might have a slightly, it could be a weak base. That's okay. But the thing you do not want to see is that the base you're using is strong. In fact, that's how you're going to be able to tell for sure whether your reaction goes the E1 or the E2 route. If the base is strong, it's going to go via the E2 pathway. But if it is a weak base, it could go via the E1 pathway. And specifically, it will favor the E1 pathway if your solvents happen to be Protic. Because if your solvent is Protic, you're going to start solvating the substrate. And specifically, because you have those big delta pluses and delta minuses on your solvent, you're going to start uh, making it not likely only, but you're going to make a good case for the CX bond right here to start developing that delta plus and delta minus charge, because it wants to increase the interaction of attraction between itself and the solvent molecules. So you're kind of facilitating that process of breaking that leaving group bonds to the electrophilic carbon. And the facilitation of lowering the energy, or making it likely that this is going to break, is the same thing as saying that the activation energy, the transition state, is going to be lower. So this makes the process go faster. At the same time, you are coordinating to your carbocation, so you are stabilizing that intermediate somewhat. Okay, so the fact that we're messing with the first activation energy, however, really determines that the Protic solvent is the solvent of choice in a unimolecular reaction. If you were to use an aprotic solvent, there will be no stabilization of the substrate trying to turn into a carbocation. In fact, because the solvent's aprotic, you really don't have big delta minuses and delta pluses in the solvent, so the incentive for this bond to want to break is not as good as it was with the Protic solvent. So this will just give you a slower reaction overall because you're not lowering the activation energy. Now the substrate, now here's where the big distinction happens between E1s and E2s. Whereas with E2, the substrate didn't really matter. As long as it had a neighboring carbon, the E2 reaction can go forward. An E1 reaction does depend on what kind of substrate you have, and the reason why is because you have to form a carbocation. And the carbocations that are the most stable are the tertiary and the secondary ones. Primary carbocations are not really good, so you're not really going to be forming primary carbocations. But secondary and tertiary, those are the ones that will lead to a lower energy of activation and also to a more stable intermediate. So an E1 reaction is definitely going to happen if your substrate is tertiary, and of course if you're hitting the reaction and you have a crappy solvent. Excuse me, not a crappy solvent, a crappy base. Um, but with the secondary ones, much like the substitution reactions, you have this kind of situation where maybe could go via the E1, maybe could go via the E2, and what will tell you what's happening is ultimately the solvent that you're using. Now the E1, however, is never going to happen with a methyl or a primary substrate. And the main reason is because primary substrates don't make up for good carbocations. And much like your E1s, your E2s, your SN1s, and your SN2s, this reaction is no exception. You want to have a good leaving group, right? Having a good leaving group means that you are raising the energy of the reactant, making the activation energy lower, making it easier for this reaction to go forward. Um, so the last point to be made is that for your E1 reactions, because you have to form the carbocation, which is a strong acid, your conditions in solution are acidic. That means that you cannot have a strong base present in solution. So any of the bases that you see here in the blue box that derive from the conjugate acids that have higher pK than water, none of these bases in the blue box can be used in E1 reactions. If you do have these bases present, then you're very likely going to undergo an E2 reaction. All right, so that's just the last thing that I wanted to point out. Now, to complete the table right here, what needs to be said for the substrate is that the substrate could be secondary, tertiary, definitely not primary. Now, secondary is the common ground between E2 and E1. So one thing that may give it away as to which way you're going to go if you have a secondary alkyl halide is the type of base that you're using. A stronger base favors E2, a weaker base is what you're going to have to use for an E1 reaction. And especially if the solvent is Protic, that is definitely favoring and tending to go via the E1 pathway. The leaving group, of course, you want it to be as good as possible in both cases. The leaving group better be the conjugate base of a strong acid. That's what makes it be a good leaving group. And the temperature you want it to be hot as well. So if we compare everything, now that we have talked about elimination reactions, we have the big table, which will allow you to basically look at a reaction and say, okay, this thing is likely to go via an SN2 reaction, or this thing is likely to go via an E1 reaction, etc., etc. You can start by looking at the substrate, and I will recommend that you do that first. That's your first the first source of analysis that you should have. An SN2 reaction can happen if the substrate is methyl, primary, or potentially secondary. An SN1, on the other hand, can only happen with secondary or tertiary substrates. Your E2 reaction can happen with primary, secondary, tertiary, but not methyl. And your E1 reaction can happen with secondary or tertiary. So the E1 and the SN1 are pretty much identical in that regard. In terms of your nucleophile or base, you want for an SN2 reaction as good a base, as good a nucleophile as you can get your hands on. And your SN1 is going to be a crappy base by default of the fact that you have to produce a carbocation in solution. Your E2 reaction is going to be favored by a strong base. The stronger the base, the better your chances of undergoing an E2 reaction. And having to use a crop base is not what favors an E1 reaction, but it is basically what you're stuck with because of the conditions of the solution, which have to be acidic. Solvent. Bimolecular reactions will always be favored by aprotic solvents, so SN2 and E2 are favored by aprotic solvents, whereas unimolecular processes are favored by protic solvents. The leaving group in all of these reactions has to be good. If you don't have a good leaving group, you have to find a means of turning it into a good leaving group. That sometimes may mean that you have to use an acid to turn that hydroxyl group into a good leaving group, or you have to convert your hydroxyl into a tosylate group. Now the temperature, and this is probably the big thing to notice. The temperature is going to be room temperature or low for the substitution reactions. But for eliminations, you want to heat up your reactions as much as possible. Probably reflux it in a high solvent, a high boiling solvent. And that's what's going to give it away as to whether you're doing elimination versus substitution. The temperature, high temperature, elimination. No heating or low temperature, substitution. And then at that point, you get into the specifics. Do you have a substrate that is primary or methyl? If so, it's SN2. If you have a substrate that is tertiary, you're doing SN1. If you are hitting the reactions that you're dealing in an elimination pathway, at which point you look at what kind of base you're using. Strong base favors E2. The weaker bases are going to be more likely for E1, specifically if the solvent is Protic. So those are the things you want to be on the lookout for when determining what's going to happen when you have two reactants combined with each other and which reaction you're going to go through. Okay, so that completes the lecture on elimination reactions. Be sure to practice your mechanisms because in the substitution and elimination reactions, knowing your mechanisms is key. And even though I just show you, what happens to those carbocations in the process of migration just by, moving them around, you still need to know how to move those curved arrows. So make sure to practice that. Okay, I will see you in the next lecture series. So take care. Bye-bye.